So we've got a lot of stuff up on the screen already. Okay, if you're going through the slides, it is slide 65, but we are modifying the slide a little bit. So it is, what is the pH of a buffer that contains 1 molar acetic acid and 1 molar acetate ion? We're given a pKa at 4.75. What we're going to go through and do here is kind of our standard solve, how we would solve everything that we've already done. Right? So you would write out your expression, your chemical reaction. It's acting as an acid. Why do we suspect we want it acting as an acid? Well, that's looking at our chemical reaction. So I've written this chemical reaction, but why did I draw it acting as an acid and not acting as a base? Where does it say acid? So we could go with acetic acid, but it also says acetate. Which one's in higher concentration? They're the same. Acetate's acting as a base. Why should I draw out the K or the acid expression, not the base expression? The pK what? A. Since you're given the pKa, it makes sense to look at the acid expression. Right? You're already given more context or more information about the acid expression. That's why it makes sense to draw that one out. We could also push and say that we want the acid expression because we're being asked to solve for pH. And what is pH a measure of? The negative log of the H3O plus concentration. So it makes more sense to be looking at the acid expression instead of the base expression. We're looking at our initial conditions. Remember, when we're given those values or those concentrations, those are already assumed to be initial. We could plug those in. We could go through and solve a Q as we've done in the past. Theoretically, the Q would be a little bit straightforward because we should recognize that we're starting with 0 H3O plus. This reaction, if we solved the Q, is going to get us a 0. K will always be larger than 0. Which means to shift from a 0 value to a value that is larger than it, we must increase the concentration of products. Which means I need a plus for my change for my products, and I need a minus for my reactants. The question is going to become, how much does it change? Well, what am I interested in solving for? pH. What is pH a measure of? H3O plus. Which means if I'm going to set up my ice table and go through all this work, I want my X, my unknown variable, to match as close to the final answer that I'm looking for as possible. So I'm going to say my H3O plus is going to go up by X. Right? I'm defining that. That's my focal point. Right? What's the acetate going to go up by? Also by X. How come it's also going up by X? Just because I increase the products doesn't mean they should increase at the same. How do I know they should both increase by the same magnitude? Coefficients from the balanced chemical expression. When we're looking at acid-base reactions, very commonly they're 1-to-1, and so we tend to lose sight of that information. And that tends to bite us when we move into KSPs, because in KSPs, it's very rare for them to be 1-to-1 expressions. And so we start to mess up and screw up our ice tables when we manipulate those. So make sure you're paying attention to what's going on within your conversions. Okay? If those go up by 1, by X, what does our product or reactant need to go down by? Also by X. Not half X. Why not half X? If those two both went up by 1, shouldn't the other one go down by 2?
The coefficient.
Again, it comes back to the coefficients of the chemical equation. Use those coefficients. That's why you talked about it and learned it in 151. If we navigate through, we would get 1.0 minus X, or CH3COO minus. It's going to be 1.0 plus X, and then we're going to get our X for our concentration. We could then go through and sub those values in. 1.0 plus X times X all over 1.0 minus X. We now have an expression, and what can we do with that expression? Solve for X. right? It's going to get a little bit messy, but you can go through and plug in numbers. You can make assumptions. The assumptions will probably hold valid, and you should be able to plug it in. What did I miss?
I mean, but it's, no, it's
Everything subs in, and now you just solve for x. Okay? You do have some messy algebra to go through and deal with, but you can do that. That's ultimately just algebra, and you would go through and get an x value. Okay? What did we say that x value was? You're like, I don't know the numerical value. I didn't ask what the numerical value was. What is the x?
Concentration of H3O.
The concentration of H3O plus. Does that answer our question? No, so what do? We take the negative log of that x, and we now have our pH. Kind of, sort of? That's a question. Okay. That follows our standard protocols for everything else. We do get a little bit messy with this algebra, and that's where other people might come in and say, well, is there something else we could do? Okay? And that something else we could do, what we're going to do is actually erase all of this work. And we're really just going to hyper-focus on that endpoint. Okay? And by our endpoint, just the K expression. Okay, that didn't work at all, so let's try that again. Let's ignore that expression. Our Ka from our equation was our CH3COO minus times our H3O plus, divided by our CH3COOH. Yeah? What are we trying to solve for? pH. And we know pH is equal to the negative log of the H3O plus. Do I have the H3O plus in my original expression? Does H3O plus show up in the Ka?
Yes.
Yes. All right, but what doesn't show up is the negative log. So how about I take the negative log of both sides? Am I allowed to do that? Yeah. Well, that seems kind of weird. Why would we go through and do that? Well, some things happen. If I take the negative log of the Ka, what can happen? I can simplify that writing, and I can write that out as pKa. Negative log of this giant gory thing looks really messy. You might be like, why would I want to go through and deal with that at all? Okay, this is where mathematics can come in and help us out. Do we have some mathematical simplification systems that we can pull? Particularly with logarithms. One option is we're just going to rearrange our Ka expression just a little bit. Right, note I just slid everything over. Is that okay? Am I allowed to do that? And then I'm going to do one more simplification. Am I allowed to do that? Okay. Why? Why should I do that? The log can distribute. Okay? How does it distribute? The negative log of the first one, cool, CH3COO minus, oops, that's a minus, over our CH3COOH, parentheses. How do I distribute it to the H plus? When we're dealing with those logs of the parentheses, it's plus the negative log of the H3O plus. And so for some people shouting stuff out, I understand where you're going, but I'm not quite there yet. Right? You might say, well, isn't that kind of weird to write a plus minus there? It is very weird to do a plus minus there, but what am I trying to emphasize? What is the negative log of H3O plus? That's the pH. So I can get the pKa is equal to the negative log. I'm going to do some simplifications here. A minus over HA plus the pH. Do I know the pKa? Yeah. Do I know the concentration of A minus in HA? Yeah, that was straight from the question. So all I got to do is plug those numbers in, solve for my pH, and I'm done. I don't have to deal with an ice table. Okay, why not? Because some smart mathematician looked at that expression and noticed those patterns and was able to pull that information out so that we could rearrange the whole starting premise into a neat equation that solves everything almost instantly. Yes, sir?
The A minus over HA, that's, what is that? I mean, it's like, obviously it's you brought it down, but it's like replaceable with just those or any?
That's kind of the beauty of this. So CH3COOH. Okay, when I went through and said A minus, I said the top was A minus. Okay, what is A minus?
The conjugate base.
It's our conjugate base. What is HA? The parent acid. Okay? So what I did was simplify it so I didn't have to write it all the way out. So thanks.
So they're interchangeable almost.
Interchangeable becomes an interesting word. Can I swap in any conjugate base, acid base pair? Yes.
Well, so then why couldn't you use the other function then? Because if negative A is HA, why couldn't you use the Henderson-Hasselbalch
What did we just solve for?
pH?
What did we just write out? Okay, so you're like, why don't we just use the Henderson-Hasselbalch? Tell me what the Henderson-Hasselbalch expression is.
Oh, yeah.
Mother, really? This is the Henderson-Hasselbalch expression.
Well, so then why are we doing it?
Okay, why are we doing it this way? Why do you think we would show where it comes from?
Understanding a little bit more.
That's all it is.
Okay.
Okay? What we're trying to say is the Henderson-Hasselbalch isn't just pulled out of thin air. It's a rearrangement of the stuff you already are aware of. Do you know what the Ka was? Yeah. Do you know how to calculate a P anything? Yeah. Do you know how to take the log of both sides? Yeah. Why would we do that, though? Why? Why do we do that? Is it sets us up with an expression that now allows us to solve these types of problems very, very swiftly. What are these types of problems? These types of problems are buffer problems, right? Which we haven't addressed as an actual term. What we just talked about is, we have these acid-base reactions. We can do acids, we can do bases, we can solve for H+, we can do all of those individual solutions, right? But in this particular case, what we're doing is now adding this extra concept of a buffer. Well, the buffer just says that I start with a little bit of the acid and the conjugate base. I have both of them present. Does that change any of the ice table rules? No. None of those rules change. All of those systems do exactly the same process. So why do I need a new process? Which was shorter, Henderson-Hasselbalch or the ice tables? Okay. Henderson-Hasselbalch is shorter, so we want to understand where it's coming from and when and why to use it. When could we use it? We had this buffer where we had concentrations of both those species. That's when. What if we don't have both those species? Then you can't use Henderson-Hasselbalch. Right? So it's trying to recognize when the value of that expression appears. And if you don't understand when it appears, you'll start to use it. When? All the time. And what you'll find is probably 3/4 of the time, I'll let you process the math on your own, if you use it, you'll be wrong because it was an improper use of that time. Right? So the intent is recognizing where it's coming from. So if you're seeing the word buffer, you can pretty much instantly launch into dealing with Henderson-Hasselbalch. Okay? It's not a perfect guarantee, but it does work out for us. I did delete everything from the slide and removed everything, and in the process of removing everything, we see what the parent question was. What is the parent question? So we're going to erase all my nice work. What did the parent question actually ask? Because the original question is, I just have acetic acid and acetate. What's the parent question ask about? Okay. This was the part that suddenly appeared. How does this change our system? What does HCl supply? Hydrogen ions. Supplies a whole bunch of H+. And if we add H+ into the system, what should happen to our pH? We add H+ into our system, our pH should decrease. We got to be aware of that negative log. This is why we could calculate things to help us out with that. Okay, and it should go through the floor really, really, really fast. Except if I add H+ into the system, what does it do to those ions? H+ reacts with, it does react with OH negative. Okay? The thing we want to back away from is the OH and acknowledge the more important part, the negative part. It would react with our conjugate base. So if I add H+, what's going to happen? This species concentration is going to decrease so that it can make up an increase over here. So an excess of that H+ is now going to mess with the initial settings. And if those initial settings are adjusted, I now need to change what I sub in for my Henderson-Hasselbalch. So if we reveal the equation underneath, if we add HCl, what happens? It reacts with the acetate that's present and turns into CH3COOH. Why does that matter? What happens to the concentration of acetate then? Started at 1.0 molar. What happens when I add HCl? What increases? What does the HCl react with? The negative species. HCl is H+, positive with a negative. And if that reacts, what happens to this concentration? Does what? That one decreases. How much is it going to decrease by? Why is it going to decrease by 0.1? It's a strong acid, which means my initial concentrations of my acetate is not 1 molar, it's going to be 0.9 molar. Where did that extra 0.1 molar acetate go? Where did that carbon go? Did that just disappear? We just took that one, destruction. Where did the carbon go? It went through a chemical reaction. Instead of decreasing, we're going to increase because our product concentration has to account for that differential. So it's going to go up by 0.1, which means my initial concentration of my acetic acid is 1.1 molar. Okay? The addition of a strong acid is not an equilibrium reaction. Okay? It's going to change the concentrations of those starting conditions. And as soon as those starting conditions are changed, we're now at a point where we could launch into an ice table. Those would be our initial conditions. And we can plug that into our Ka expression. Do we want to deal with a big ice table? No. So what can you do? Sub them directly into your Henderson-Hasselbalch expression. So what's the concentration of the acetate? 0.9. What's the concentration of the acetic acid? 1.1. Do we know what the pKa was? Yeah, it was 4.75. Can you solve for the pH now? Yeah. Right? So the point of this is to recognize that as soon as you have a buffer, it's going to do a chemical reaction with any strong acids. Strong acids are not equilibrium. They're going to go in and destroy your initial settings. Those initial settings are now reset after that chemical reaction. Now you can go through and say, well, what do I have? How can this navigate through my system? Kind of, sort of? This is a pretty powerful expression and allows us to go through and do lots of kind of cool things. Those cool things typically show up, for those of you that have to continue, in organic chemistry a little bit, and then to a much larger extent for anybody going through the pre-health type profession in biochem. Biochem exploits this expression to no end, and it makes it a lot more challenging to manipulate. If you don't need it, then if you don't need biochem or ochem, do you still care? Like, nope, I don't care. It's on your quiz. So yes, you do care. You need to be able to use it. Okay? So you need to be able to understand and manipulate those expressions. Okay? So if we go through and look at this, a buffer solution contains 1 molar acetic acid and 1 molar acetate, conjugate base, calculate the pH of the solution. We can just plug and chug with our Henderson-Hasselbalch. That's kind of the beauty of this system. Right? We technically already did that. That's what we started the class with, so we don't need to go through and solve that. Right? This expression is very important. Very important. I wanted to make sure that we covered it at the beginning of class instead of maybe dragging it through to the end of class. Do we have questions about this expression and its manipulation? Go ahead.
What are the 2 little lines next to the A?
I'm not positive how that happened, but that is ultimately just a typo. Should just be 1 minus. Right. I will say that I've seen some expressions when we talk about A minus being equal to base and HA being equal to acid. We do have to be a little bit careful with those names, okay? Because in the previous question that we looked at, a buffer solution that had 0.1 molar HCl added to it. Does that 0.1 molar show up in your Henderson-Hasselbalch expression? No. Okay. What shows up is the conjugate acid-base pairs. HCl isn't a conjugate acid-base pair. HCl is a strong acid. It doesn't show up in the Henderson-Hasselbalch expression. It's only the weak acids. Okay? Questions about that? Okay. Which then means we backtrack to where we left off. Come on, pencil, pen, screen, do what I want. This is where I believe we ended last week. Right? So carbonate is a weak base. Write the reaction that occurs between carbonate and H3O+. Just write it out. It's a blue box. You can talk to your table if you've got questions about it. When we're talking about this chemical reaction, we want to react the CO3 minus 2 plus H3O plus, because that's what we're told to go through and do. How should the CO3 minus 2 act? How should the carbonate ion react? Go for it again.
As a base?
Base. How do we know it should act as a base? It says base. Awesome. Do better. H3O plus is by definition an acid, which means CO3 minus, or our carbonate, must act as a base. Okay? Is there another explanation? Yes. Why else should this carbonate ion act as a base and not as an acid?
Because it doesn't have an H plus ion.
To act as an acid, it must have H+. It must have a hydrogen ion, and carbonate does not. So we've got lots of evidence that suggests our carbonate's going to act as a base. what's going to happen is we're going to transfer a hydrogen. When we're talking about these chemical reactions, we want to keep it limited, just single hydrogens. HCO3, and then we get H2O. What's wrong with what I've drawn? Say again? There needs to be a negative charge. I started with 2 negatives and a positive, which means I need to end with that same balance of charge. The balance of charge was a -1 on my reactants, which means the products must also have a total of -1. Should the water be a -1? Nope, water is neutral, which means we're missing, come on, pen. We're missing the negative on the other species. This is dealing with those charges. Are those charges important? Yes, they dictate all chemical reactions. So if you're going to be asked to write out a chemical reaction and you don't show that charge, you will be marked wrong, aggressively so. Okay? Those charges are very, very important. Make sure you nail them down. Okay? The follow-up question, because you've now got the chemical reaction in front of you, I can delete it, is write the equilibrium constant expression for this reaction. Okay? This one gets a little bit weird, because I would argue it's not a true equilibrium that we're dealing with here, because we're looking at that strong acid. But we should be able to write out that equilibrium expression. Okay, so we should get that for our equilibrium expression. Okay, it's our products over our reactants. It's a -2 there. The water doesn't show up in our expression. Why not? Water is a liquid. Why do liquids not show up? What's constant? What's constant? What part of water is constant? The concentration. So it's again going back to the stuff that we talked about in Unit 2, and you're applying that back into this system. Okay, and this sets us up with an equilibrium expression. Okay, what can we do with that? How does a decrease in the pH affect the solubility of calcium carbonate? We've got 2 expressions or 2 reactions drawn below. Okay, which of those 2 expressions is the question asking about? Said potentially a different way, what is the question asking about? Some people are mouthing it, so we'll take that as a out loud expression. We're looking at the solubility of calcium carbonate. Which expression looks at the solubility of calcium carbonate? The second expression. So this question is only really centered on that second expression. Okay, this is the whole point, this second expression. Okay, then it says, how does a decrease in pH? What the heck does a decrease in pH mean? Okay, a decrease in pH means more acidic. What does more acidic mean? And don't say decrease in pH. What would H3O plus react with? Generally speaking, what does a positively charged molecule react with? A negatively charged molecule. So we can now go down to our important chemical expression. Where do we see a negative molecule? The carbonate. So we could react the carbonate with that H3O plus, and we could be looking at a downward chemical expression because of where it's written. What would our products be? It would be HCO3. I can't, sometimes. Plus our H2O. Does that expression look familiar? What does this look like? It looks like the previous expression that we had on the previous slide. It also looks like the very first equation given at the top. So what you're being asked to do is interpret the language of the question and then be able to reference to the proper equation systems that are necessary to go through and solve. Okay? Why has it become important? Because we're given some information about it. We're given a K. What does that K mean? What is the size of that K? When we talk about Ks, there's really only two types of Ks. What are those two types of Ks? This goes back to Unit 2 or even this expression. K is either greater than 1 or K is less than 1. Those are our two options. If it's greater than 1, what does that mean? Product favored. If it's less than 1, what does that mean?
Reactive favored.
If we look at this K, what do we see? A K that is
Product favored.
product favored, which means when we look at this chemical expression, we aren't really looking at that as a true equilibrium. We're really looking at it as a unidirectional. Okay, since it's unidirectional going towards the products, because we've drawn them downwards, what does that mean for us? What happens to the concentration of carbonate when I increase the concentration of H3O+? It decreases. The H plus will react with whatever carbonate is there and remove it from the solution. What I've now just done is a stress to the system. We've just done a little bit of a Le Chatelier system. We've decreased the concentration of carbonate. What does our chemical reaction do to alleviate that stress?
The reaction quotient shifts.
Okay, the reaction shifts to do what?
Increase the reactants.
Does it increase the reactants? If our product concentration goes down, we start at equilibrium, and we take a chunk out of our product, are we going to be balanced? No, so what has to happen?
Shifting more products.
I have to shift, I have to take a chunk of these and turn them into products so that it's now rebalanced, which means my reactant concentration would go down. Okay? So that I could get that product concentration back to where it needed to be. When we're talking about our reactant here is a solid, so it never shows up in the chemical expression, but what does that mean about its ability to dissolve? If its quote-unquote concentration goes down, we're getting less solid and more aqueous. Which means what happened to the solubility? Did we increase dissolving things or decrease dissolving things? We increased, which means the molar solubility goes up. By adding acid into the solution, we increase the probability of converting that solid calcium carbonate into a solution. It dissolves. That's what this system is trying to tell us. So what we're trying to do is now fold in all of this information that we've been working with. We've got KSBs, we've got pHs, and we're trying to show how they're all interconnected. Okay. Why do we care that calcium carbonate dissolves more under acidic conditions? Okay? We care about the oceans. Okay? But if we're going to become an electrical engineer, sorry, I don't have anything for electrical engineers, but maybe mechanical engineers or materials engineers, okay? Or civil engineers that are looking at the building of roads. Why would we care? Where else is calcium carbonate used? Concrete. Why is that a problem? If we start to get acid rain, what happens to our concrete? It dissolves. Well, who cares? Our statutes didn't need to be all that important anyway. What the hell are our roads made out of?
Asphalt?
Think about our major roads. Our major roads are actually not made out of asphalt. They're made out of concrete.
They're not supported by asphalt.
right? Our concrete has a lot of calcium carbonate in it. That's part of that chemical structure. And if we start to change the pH, we're going to start messing with our roads. Right? We're going to start messing with our buildings. We're going to start messing with statues if we've got those around. Right? And so it's a really important aspect to deal with. If we push, we're messing with the oceans. The oceans is the largest part of our freaking planet. If that gets messed up, that messes up a lot of stuff. Right? So we want to be aware of those conditions and be able to study them so that we can understand what's going on and how our effects, how what we do can affect those systems. So we could go through and look at the molar solubility. At a pH of 8, we're looking at 10 to the minus 4. When we drop to a pH of 7, are we acidic? No. Are we more acidic? Yes. So what we care about is that transition. We aren't saying we have to be acidic. We're just saying if we're more acidic, we're going to change the solubility. How did we change the solubility? We went from a 4 to a 3. It decreased, right? It increased because it's not a 4 to a 3. It's a negative 4 to a negative 3. We have to deal with our powers of 10, right? In dealing with those interpretations. So the solubility of our ionic compounds is greatly affected by our pH, particularly if they contain weak acids or bases within their chemical formulas. Right? So you probably ran lots of chemical reactions within Alex talking about common ion effect. If we add a base, what happens? If you add an acid, what happens? Right? Here all we've done is quantify that effect. Kind of, sort of? Okay. So, how could we use this necessarily in our everyday lives, sort of? Right? If we looked at our shower heads or even our spigots, you might see this kind of accumulation of gross stuff on it. And you'd be like, oh, that's gross. I need to get that off. How do you get it off? You can go to something like CLR. What is CLR composed of? Acid, an acid, an acid, and another acid. CLR has tons of different acids in it. Because what we're trying to do is to drop that pH to increase the solubility of that solid scale. That scale is a calcium carbonate or a carbonate type structure. So what we're trying to do is dissolve that off so it looks better. Right? You could equally do it with vinegar, right? Which is primarily just acetic acid. Right? And then your house smells like salad dressing, which, depending on your perspective, is a good thing or a bad thing. Okay? So our acid-base reactions are equilibrium systems. Okay, so all we're trying to address is that when we look at a Ka expression, okay, or even a Ksp expression, we can think about how changing the concentration of any of the individual species within it can change our overall expression. Why do we not look at changing the concentration of water? Shouldn't that have an effect? Or your Ka, or your Kb? No. So changing the concentration of water isn't really going to have an effect, okay? Because the concentration of water is constant. Okay? We ultimately can't change its concentration because it's a pure liquid. Okay? So if we're looking at this system and we decide that it is at equilibrium, what we could then talk about, okay, is what happens if I add more acetic acid. Well, what happens if I increase the concentration of acetic acid? What's my equilibrium going to do? It has to get rid of that increase by shifting to form the products, which means, right, we're going to see an increase in the concentration of the acetate. We'll see an increase in the concentration of H3O+. And because concentrations are this nebulous thing that we don't want to discuss with the real world, we instead convert the concentration into pH. So we could then go through and say, well, if the H plus increased, our pH decreased. And we have to be extra careful to interpret those and recognize what those things mean. pH isn't something that shows up in your chemical expression. H3O plus is. So if you're being asked to explain something, you should talk about the thing that appears in the work that you're doing. Okay? Make sense? Okay? Which then takes us to the next system. A buffer is a solution that contains approximately equal amounts of the weak acid and its conjugate base. Okay? This is why we could use the Henderson-Hasselbalch when that comes in. Okay? So we have equal concentrations, more or less. What is the point of the buffer? What is the point of a buffer? What is it going to do? It prevents large pH swings. So if we just had water and added acid to it, what happens to our pH? What happens to the pH if you add acid to water? It decreases, and it decreases very, very, very rapidly. But if I have a buffer and I add H plus or H3O plus, what does that do? Well, that positive is going to react with the negative. That's going to cause the equilibrium to shift towards the reactants. I get an increase in the HA, and at the same time, what's going to happen to that extra H3O plus that I added? Its concentration drops. And if its concentration drops, what happens to the pH? It won't change as much. Right? Is it still going to drop? Yeah, because it's a weak acid-base equilibrium. So adding extra H3O plus is going to drop the pH, but some of that effect will get buffed away by the conjugate base reacting with it. So the point of a buffer minimizes drastic changes in H plus or H3O plus. Right? So that's pretty cool. What else can it minimize? It can also minimize the effects of strong bases being added, because a strong base is ultimately going to supply us with hydroxide. Well, that negative charge on our hydroxide is going to want to react with what? Our weak acid. So what happens? The addition of that hydroxide would drastically skyrocket the pH, except that our weak acid will absorb some of that, dropping its overall concentration and increasing the reactants to buff out that change in pH. Okay? Again, it doesn't completely wipe it out. Okay? It can't completely wipe it out because they're looking at a weak equilibrium. But what it does is it minimizes that change. And as long as we have the conjugate acid-base pair, we can buff out either direction. We can minimize the effects of base. We can minimize the effects of H3O+. Okay? Why is this important to us? All life is maintained at a constant pH. That constant pH is not the same for each form of life, and even with an individual organism, it's not the same. Okay? For those of you that have gone through and done biology classes, if you look at the pH of your muscles versus your lungs, they're different. Why? What are your lungs trying to do? What do your lungs do? Bring oxygen in, cool. That's all they do. They just bring oxygen in.
Supply to the bloodstream.
They supply it to the bloodstream. Okay, so there's going to be a chemical reaction there that is going to be pH dependent. What else do they do?
Get rid of carbon dioxide.
They get rid of carbon dioxide. Is carbon dioxide, particularly its reaction with water, an acid-base reaction? Yeah, it's going to change pH. So if we look at what your lungs are trying to do, you're trying to get CO2 out of the body. You're going to change the pHs to minimize the solubility of CO2 in your bloodstream. What are your muscles trying to do? They're just moving. But to move, they need to burn energy. They need to do a combustion reaction, which means what are they producing? CO2. If that CO2 builds up in your muscles, it's kind of like death. Okay? So we need to get that CO2 into the bloodstream. So we actually want to increase the solubility of CO2 to get it into the bloodstream so that it can then move around back to the lungs that now can change the pH to expel it. So you'll change the pH in those individual systems to change the transport of individual gases. That's pretty freaking powerful. Right? If we go through and look at ecosystems are all set up around a particular pH. Right? You can look at hot springs. Hot springs have fairly low pHs, I believe. I'm not positive on that, don't quote me. Right? Those low pHs would kill most life, but there are forms of life that do exist there. And if we take them out of that system to study them and put them into our water, what instantly happens? They die because we've changed the pH and the temperature. Okay? So we would need to ensure that if we're going to study those different systems, that we have to maintain their pH system. Okay? That's the point of our buffers. All systems have buffers in place to minimize those drastic effects, because those changes will ultimately change the structure. Ooh, that's fun. It's out of sync. Come on. Right. How does it change the structure? We can do, actually, we'll go to Henderson-Hasselbalch, because I don't think it's in the slides, so we'll talk through it real quickly. We're talking about life. Life as we know it is based off of several components. What are some of those components of life? Just hoping for it and see what happens. How do you get stronger? Just food? What's that? Water? I drink lots of water. I'm not getting any stronger. Protein. What makes up proteins? Amino acids. So if we go through and look at an amino acid, we have an amino end and we have an acid end. Okay? Officially, amino acids also have a side chain. This side chain could have an acid-base effect as well. Okay? Amino acid. Okay? It is listed out here this way. This is an amino and this is an acid. Is that acid a strong acid? If you're like, well, how would I know that? Remember how I said it would be a really good idea to memorize your strong acids? Because if you had those memorized, you'd have your way around certain questions like, is this a strong acid? No, it's not a strong acid. It's not a strong acid, it's a weak acid, which means its protonation state is dependent on the pH, okay, and its pKa. So I could look up the pKa for this acid being about 2, and if I change now my pH, if I go to a pH of, say, 7, that's neutral. That shouldn't really have an effect. Well, plug those values into our expression. pH equals 7, pKa equals 2. What happens? Guys, so there's some concern on that. We'd say 7 equals 2 plus the log of A minus over HA, right? 7 minus 2 would be, it's 5, which then equals our log of our A minus over HA. Do you like logs? No? How do you get rid of logs? Power of 10 of both sides. So 10 to the 5th equals A minus over HA. What does that mean? Is 10 to the 5th a big number or a small number? It's a big number. What does that mean about A minus versus HA? A lot more A minus. So if I'm at a pH of 7, what could I predict about my acid? I need to be the A minus state. What do I need to do? Remove that hydrogen. That's a structural change. That structural change changes the intermolecular forces, which changes how the protein folds. I could equally do that on the amino side, right? And try and manipulate what's going on that side. That one gets a little bit trickier and starts to mess with A minus protonated, deprotonated state, so I'll leave that for your organic chemistry class if you need it. Okay, or biochem. but you're ultimately going to go through and do a very similar process on the other end and decide what your protonated versus deprotonated states are. Right? Why does this matter? Well, that was a pH of 7. What if I made the pH 10? How is it going to change my results? An even bigger A minus. What if I make the pH 1? If we make the pH of 1, how does that change our calculation? That becomes 1. 1 minus 2 would be negative 1. What does that mean?
More
I now have more HA than I have A, which means what happens to my structure? I need to have the hydrogen back on the structure. So the protonation state is heavily dependent on our pH, okay, and technically the pKa. It's the interplay between those two. This is where Henderson-Hasselbalch as an expression really shines and shows its utility. Calculating pH ultimately isn't all that useful. What is useful is understanding the concentration or the relative concentrations of your conjugate base and your acid. That becomes huge because that allows you to predict individual charges. Right? And if you take this all the way up to biochem, you have to look at an individual amino acid, is what we're looking at here. In biochem, we don't care about individual amino acids, we care about lots of amino acids. So they could give you a string of 10 amino acids and say, tell me what the charge is at pH 5. You would then evaluate pKa to each of those individual acid groups to determine what its charge would be, and then you take a look at the total charge for everything. It's a more extensive process, but ultimately all you're doing is a manipulation of Henderson-Hasselbalch, which is pretty sweet. Okay? So what is the ratio of CH3COO minus to CH3COOH when the pH equals 3.5 and when pH equals 5.75? We just set up a rough expression on how we could go through and solve it. You should now be able to do this on your own. Talk at your tables, try and figure it out. If we set up our system, we're going to get -1 equals our log of CH3COO minus over the CH3COOH. We're going to get 10 to the negative equals our CH3COO minus over CH3COOH. What does that mean? Or 1 to 0.1. What does that mean? What does it mean? Right? This means the concentration of CH3COOH is greater than the concentration of our CH3COO minus. Okay? That's going to be the relevant piece of information. If we go through and look at the other side, what do we get? 1 equals log CH3COO minus over our CH3COOH. If we push that all the way down, we're going to get 10 to the 1. Which means what? I now have a greater concentration of the acetate than I have of the acetic acid. Kind of makes sense? So what you're trying to manipulate is those individual relationships and see how that manifests at the overall equation. Cool? As I'm seeing some writing, I'll wait a second and just kind of pause. Okay. Buffers are most effective when your pH is plus or minus 1 from the pKa. Okay. Why? Why does it make sense that your buffer is only effective in that range and not outside that range? What happens when you go outside that range? If we go to a pH that is 2 lower than the pKa, what does that mean? If I go 2 lower, am I more acidic? If my pH is 2 lower, I'm more acidic. Since I'm in that more acidic environment, what's happening to the concentration of my A minus?
100 times the
If I have 2 times, or go down 2 times with H plus, so more H plus, what does the H plus react with? Does the H plus react with A or with HA? Reacts with A. So if I'm at a pH that is 2 times lower, or not 2 times, but 2 units lower, okay, that means the concentration of A minus is doing what? Decreases. The A minus is now going to go through the floor. Okay, so I'm going to have a very small amount of A minus and a large amount of HA. Right? If I go 2 times, I've gotten rid of almost all of the A minus, if not all of the A minus. And if all of the A minus is gone, do I have a buffer anymore? Nope. So that buffer system works only because I have concentration of A minus and HA. If I push outside that realm, that's when I start to lose the ability to buffer because I no longer have a buffer system. I don't have a mix of each of them. I've added so much acid that I've converted all of the A minus into HA. There's now nothing left to minimize the effect of H plus. If we flip it and look at the other direction, if I now increase the pH, we're talking about having more hydroxide ions present. If hydroxide comes in, what's the hydroxide going to react with? The hydroxide will react with HA, which means what happens to the concentration of HA? That's going to fall off. And if there's no HA left, there's nothing to mitigate the addition of more base. So the buffer works because I have the counteracting ion present. If I don't have that counteracting ion present, I've lost it. Okay, I've lost that ability to buffer. Someone has gone through the calculations and found out where that line is, and it's roughly plus or minus 1. Right? Once you've shifted a pH outside of that range of your pKa, you've now lost your ability to buffer, and now you're going to see massive swings in your pH. Whoops, come on, button. Okay. So, yeah, what happens to the pH of a buffer when a strong acid such as HCl is added? Right? If we were to write out the chemical reaction when HCl is added to water, what's our chemical reaction look like? There's some subtle things that we would go through and do. So number 1, we would have HCl. We'll help you out a little bit. You said you're tired. Plus water. Okay, what does this go through to produce? Chloride ion and H plus. The important thing to note, well, actually we'll come back to the important thing to note. What happens if I go through and I add it to acetic acid? Okay? Or technically the buffer system. What is the HCl going to react with? Does it react with the acid, HA, or does it react with its conjugate base? It reacts with the conjugate base. Right? In both cases, those are not equilibrium systems because we're dealing with strong acids. But in the second case, what's powerful is that once that reaction has happened, if we still have concentration of CO3 minus and our CH3COOH, what could we, God, where's that freaking formula? Right? If we still have those concentrations, we could go through and evaluate a K expression. Okay? And if we want it to be the Ka, we could say how the acetate interacts with water, or acetic acid interacts with water to form our acetate plus our H3O plus. This sets us up with a Ka. That Ka, we could use our Does the chloride ion act as a buffer? No. Does the water? No. So what happens to the pH? The pH will be exactly what the H3O plus was. There is no buffering of that system. So when we add a little bit of acid to a buffer system, the acid goes through a pre-reaction with whatever species we're going to be dealing with. So in this case, the conjugate base. That's going to change its initial concentrations. Those initial concentrations we can plug back into an equilibrium Ka expression. How do we know it's an equilibrium Ka expression? Because we should be showing a double arrow. How do we know the top one's not in equilibrium? It's a single arrow. Okay? We know it's a single arrow because it's a strong acid. Kind of, sort of? What do you need?
Do you know where Nelson is?
Where who?
The person that
Oh. Okay. Oh. If you're picking up stuff from Mel, you probably want our notebook too.
Oh, yes. Thank you very much. Have a good rest of your day.
Is she just outside?
Yeah, I have an migraine and all that. So I can just get
What happens to the 0.1 molar HCl? All of that converts into H+, which means what do we do?
Increase in H3O plus.
Yeah, how do you calculate the pH? pH will equal negative log of 0.1 because it fully converts. Okay? Non-equilibrium, we don't worry about it. Okay? What happens in this case when we add it to an acetic acid buffer? First, we run a non-equilibrium reaction. The HCl reacts with the acetate ion. That acetate ion concentration is now going to change. It has to decrease because it's reacting with that HCl in a non-equilibrium type system. When it reacts, the concentration of our acetic acid will go up. The acetate goes down. We get new initial conditions. With those new initial conditions, we could now deal with an equilibrium system, and we would go through and calculate the pH. That should be really familiar. How could we calculate that pH? Henderson-Hasselbalch, or dealing with an ice table. And if you're wondering how to go through and do that, that was literally our first 15, 20 minutes of today's lecture. Okay, so you can go back in the video to the very beginning. Okay, so the pH of your buffer changes only a little bit when a strong acid or base is added, and that's because the H3O plus reacts with your conjugate base, okay, which means if the H3O plus disappears from the expression, your pH shouldn't have an effect. If we look at adding a strong base, the strong base reacts with the acid of our buffer system, removing that hydroxide concentration. If we limit the effect or the presence, come on, pen, of either the hydroxide or the acid, we would expect a relatively minimal change in our pH. This is the point of our buffer. That's what it's trying to go through and do. Right? Your body contains buffers all over the place. Okay? Again, to maintain that pH in different environments. We talked about that with dealing with lungs, trying to transport CO2 from your muscles to your lungs. Okay? You can look at it in your stomach. Okay? What's your stomach trying to do? Break down everything. Okay? So our bodies already have a very balanced pH system in place. Okay, why does that become important? Well, if we look at this water is fancy and expensive because it's alkaline water. It's normal water. They even say it in the statement. Okay? It's normal water where they've changed the pH to a higher level, so it's slightly basic. Why? Because basic water is going to make you healthy. No, basic water is just going to change the pH of your stomach. Okay? And even then, is it going to change the pH of your stomach much? No, because what's your stomach supposed to do? Be acidic to dissolve everything. Okay? So drinking alkaline water doesn't change your buffer system, okay, at all. Okay? What does it do? shrinks your wallet. That's about it. Hooray! Yes.
Are you then advocating for acidic water?
Nope. Nope, I am not. Okay, what I'm advocating for is water, clean water, which is becoming less and less common. Yes. No, I was just scratching it. Okay. Okay. Which then I'm going to get kind of excited about, and potentially you will too, because I believe, well, almost. Okay. How to make a buffer. So if we want to make a buffer at pH 9, okay, remember, we want the buffer to hit roughly our pH line. So if we're going to look for a buffer for pH 9, which pKa should we pick? One that is as close as possible to 9. So we look at our buffer list, which one hits a pKa of about 9? The NH4, that's going to be our best buffer to target that pH of 9. That was that whole point of that slide earlier. Where'd it go? This one. Your buffer is most effective when your pH is plus or minus 1 from your pKa. So if I want a pH coming in at 9, if I want it to actually be a good buffer at that pH, I need a pKa that comes close to matching that. That's the whole point. Kind of, sort of? Okay. And then the super exciting thing, we're done. Hooray. You've got a quiz